Okay, now we're recording. So I introduce you again. So it's a pleasure to have Eric Mefford from École Polytechnique, who will tell us about transporting clean quantum critical superfluid. So great. Thanks a lot, Eric, and start whenever you want.
Thanks. So first, I'd like to thank the organizers for putting together this great web series and keeping us all engaged during these challenging times. And thanks for the opportunity to speak to you today. So today I'm going to tell you a little bit about some ideas that I've been thinking about with Blaise Gutierrez on transport in superfluids, clean superfluids, so translationally invariant, near a quantum critical point or phase. So superfluidity is a very old subject. It was discovered 80 years ago. And I think, as a community, we understand it pretty well. So what I hope those of you in the audience get out of my talk today is, if maybe you're not so familiar with superfluidity, you can learn some of the basics today. And if you are familiar, maybe I can convince you that there's still a lot to be learned. And I think part of the reason why there's a lot to be learned is actually it's pretty difficult to experimentally observe superfluidity. And a testament to that fact is that although helium was liquefied in 1908 and superconductivity was discovered in 1911, it took another roughly 25 years before we actually observed superfluidity in helium-4. That was done by Kapitsa and also by Allen and Meissner. And then it took another 35 years before we observed superfluidity in helium-3, which is a fermionic system. And in many respects, these are the two simplest systems. They're helium's a noble gas. It's very light, and it remains liquid to very low temperatures. That's in contrast to, for instance, like hydrogen, which because of attractive interactions becomes solid at low temperatures. But it may surprise you that actually helium is the only system in which we've actually definitively observed superfluidity. I should say that we expect superfluidity to occur in lots of other systems, for instance, in nuclear matter, and there's some convincing evidence that we probably have observed it in neutron stars through what are called pulsar glitches. So here is a plot of the rotational frequency of the Vela pulsar, and over time, the rotational frequency decreases through radiative effects. But every once in a while, you see what's called a glitch, where the rotational frequency accelerates very quickly and then goes back to decreasing. And kind of the theory for why this happens is that neutron stars are thought to have a superfluid core, but the outer layers are not superfluid. And so the outer layer starts to decrease its rotational frequency, and that doesn't affect the core until, every once in a while, the core is able to dissipate some of its angular momentum into the outer layers, speeding up the outer layers. That's the glitch, and then it goes back to decreasing. So why is it so difficult to observe superfluidity? You might think that all you need for superfluidity is just the macroscopic occupation of some bosonic ground state through Bose-Einstein condensation. And it's true that that's necessary, but Landau made an argument for why that's not sufficient. And so, when we spontaneously break a U1, it gives rise to a Goldstone mode. And it's the dispersion relation of this Goldstone mode, or the fluctuations on top of the Bose-Einstein condensate, that determine whether the system is actually stable to superfluidity. And the argument that Landau gave is actually that if you look at the dispersion relation, so here's the dispersion relation for helium-4, this is experimental data. If there's a point on the dispersion curve where the tangent can be connected to the origin with a finite slope, then you actually have to put a finite amount of energy into the system to disrupt superfluidity. If, on the other hand, for instance, for a free particle, if the tangent doesn't have a finite slope, then any perturbation will disrupt superfluidity. And so here in the experimental data, you can see that helium-4 satisfies this criteria because the slope here is finite. And in addition, we can actually look at this curve and see that there's really kind of two components. When people talk about the dispersion relation for helium-4, they usually break it up into two modes. One's called the roton, which is up here. The other is the phonon. And we can think of these as a superposition of two modes, where the roton is gapped out at low energies. So really, when we think of superfluidity, we think of a system which has some low energy mode, which has a linear dispersion, and we're going to call that the phonon. The slope of this dispersion relation is just going to be called the phonon speed. A nice phenomenological model that we're probably all familiar with is to think of things in terms of an order parameter, which is a complex scalar eta, whose modulus tells us whether we're in a symmetry broken or a symmetry unbroken phase. And we usually model this in terms of this complex scalar in some Mexican hat potential, and the phase becomes the gapless Goldstone boson in the symmetry broken phase. So for our purposes, we want to think about transport in these systems, and the way we're going to do that is through hydrodynamics. And very shortly after the discovery of superfluidity, Landau and Tisza wrote down a nice hydrodynamic model that describes superfluid helium-4, goes under the name of two-fluid hydrodynamics. As per usual, we start with conservation laws, so conservation of a stress tensor and of a U1 current. Here on the right-hand side, I've included a potential background field strength. And what two-fluid hydrodynamics does is it writes the U1 current in terms of two components. The first component we'll call the normal component. It has a density, a charge density rho n, and a flow vector u. And this component is defined by the entropy current. So it's the normal current that actually causes dissipation, not the superfluid. And so this u is really coming from the entropy current. And then there's a second fluid, which is the superfluid, and it has its own velocity, which may or may not be equal to the normal velocity. Then there's a constitutive relation for the stress tensor. It has, in terms of the normal component, what looks like a perfect fluid form, and then there's another component which comes from the superfluid. Here, we have to be a little careful because this En, the energy density, is actually the energy density of the normal component, which satisfies a Smart relation of its own, and then there's a Smart relation for the full energy density, which is defined in terms of the total charge density. And the total charge density is just a sum of the normal charge density plus the superfluid density. And so these kind of serve as definitions of two quantities, the normal density, the superfluid density. That's going to be one of the main observables we're interested in. So far I haven't actually told you about how to tie our phenomenological model to this hydrodynamics. And the way I like to think about it is in terms of the free energy or the grand potential. In the symmetry unbroken phase, we know we can just write the potential in this form. And now we want to ask, how do we include the Goldstone? And to do that, we start with the realization that the Goldstone is a compact field, which means it's only defined up to angles plus multiples of 2 pi. And that means if we compute a contour integral of the gradient of phi around some curve at infinity, that defines a boundary condition. And you can have winding, so that's denoted by this alpha. And we know that we need to sum over this winding. And when the system is, when the volume is infinite, then this winding can be a real number. Now, the important point of this is that the winding is proportional to the gradient of phi, which is good because even when we break the U1 symmetry, we still have a residual shift symmetry. So we know we should really, our variable should really come with a derivative that respects that symmetry. But the Grant potential is a scalar, so we have to square the derivative. When the background field, well, when there's no background field strength, then we can treat the chemical potential for the charge as being the time component of some gauge field. And when we do that, we have to write things in terms of a gauge invariant quantity. So instead of using the gradient of phi, we should use the covariant derivative of phi. So I'll usually denote that by this xi mu. It's defined by the covariant derivative. This gives rise to two new relations. The first relation is called the Josephson relation. So written in a gauge invariant way, it just says that the time component of xi is given by minus mu, which you can see from this relation and from the definition. And then this is just saying that the pressure is a function of the temperature, the chemical potential, and then a chemical potential for the Goldstone, which is just the spatial component of this xi vector. And finally, on the previous slide, I wrote everything in terms of a velocity vector, and that can be defined in terms of this xi mu just by dividing by the chemical potential mu. To actually calculate the retarded Green's functions, we need to look at fluctuations. And so starting now, I'm going to work with the system when the superfluid velocity and the normal velocities are aligned, which means that this spatial part of xi vanishes. And I'm going to write everything in the in the fluid rest frame and in relativistic notation, although all of this can be applied to non-relativistic systems as well. So here are the fluctuations. We plug these into our conservation equations, and after some algebra, you can get this somewhat simple expression. In the limit that the temperature goes to 0, this term goes away, this term goes away, you're left with this term, and this term. And then if you commute partial derivatives of the Goldstone part of xi, you pick up factors of fluctuations of the field strength, and you can convince yourself, also using this relation, that as the temperature goes to 0, you get this really simple expression, which says that the 0 temperature normal density times this time derivative of a certain combination of the fluctuations vanishes. And this looks somewhat constraining. For a long time, people looked at this expression and thought that this told us that the normal density at 0 temperature has to vanish. And the reason they did that comes because of our experience with actual experiments on superfluids. So if we go back to helium-4 and try and calculate the normal density, remember at low temperatures and long wavelengths, low energies, we can think of the system as being just the superfluid phonon. And so the occupation of the different momentum modes is given by the the Bose distribution. And we can calculate the pressure, just like we would do in our undergraduate stat mech class, which gives, so this is in 4 dimensions, 4 space-time dimensions. This gives the pressure goes like the temperature to the 4th over this superfluid sound velocity cubed. The entropy is just the derivative of this with respect to the temperature. That gives this expression. And then to calculate rho n, we can think about the expectation value of the momentum. Any momentum has to come from difference, from the difference between the normal velocity and the superfluid velocity in the rest frame of the superfluid. And you can convince yourself that when the background normal CS is CS is the superfluid sound, right? When we work in the background where these two are aligned, then at leading order, rho n is given by this expression. So you get a derivative of this distribution. And then you can see that delta V appears square to both of these, so it cancels out. And you end up with something that goes like t to the fourth over cs to the fifth. And this is exactly given by s times t over cs squared. So in particular, the normal density, here's a plot of the functions, the normal density vanishes at 0 temperature, and it vanishes in a very specific way. Now, we can look at other examples. So for instance, in a relativistic system in our phenomenological model we looked at earlier, you can calculate the dispersion relation, which gives a superfluid sound of this form. And then you can calculate the pressure. So to one loop order, it has this form, which to leading order in grad phi, which in the background vanishes, goes like pi squared times t to the fourth over 90 cs cubed. This is exactly what we saw before for helium-4. And the entropy has this form. You have to be a little careful in the relativistic version because here things are defined in terms of currents, and the current is defined with respect to derivatives of grad phi. So rho n actually has some extra dependence. It's not exactly given by st over cs squared, but you can tell that in the limit that m goes to 0, which is the limit that this theory becomes conformal in 4 dimensions, you get exactly st over mu over cs squared, and there's an extra term which is just 1 minus cs squared. You don't need to work with this particular model. In fact, it's sufficient to work at the level of a quantum effective action, which you can write in terms of some equation of state, P, for this chemical potential for the goldstone. So again, if we, for instance, work with conformal matter, P should be given by the chemical potential raised to the power d+1, and you can calculate that rho n, in this case, is given by st over mu times 1 minus cs squared over cs squared. So again, in these systems, the normal density vanishes at 0 temperature, and it does it in a very specific way. And in fact, this is true even for fermionic systems. So for instance, you can look at a BCS superconductor, which is similar to a superfluid. There's a little extra structure because of the Fermi surface. But here you can find still that the normal density goes to 0 at 0 temperature, and it does it roughly like st. So rho n is given by an integral over this function. Here I've just plotted it rather than writing it out. And you integrate over this c. This c is not this c I wrote before. It's essentially the net energy. The width of this function is roughly order the temperature. And then as you go to 0 temperature, it decays exponentially in a way just like the entropy. So again, the normal density vanishes at 0 temperature, and it seems to do so in a very specific way, which is usually the entropy times the temperature with some coefficient, and that coefficient is superfluid sound. But does this have to be the case? And so, for a long time, we just had these examples of superfluid helium. And so when we looked at that equation, it seemed natural for rho n of 0 to vanish. But with the discovery of high temperature superconductors, this expectation was kind of put into question. So in particular, this experiment by Bozovic et al. In 2016 looked at hole-doped cuprates, hole-doped LSCO, in the very overdoped regime. So over here on the phase diagram, where above the superconducting dome, you're in the putative Fermi liquid state, and here you can see actually this P corresponds to this whole doping. You start at roughly 0.16, move this way, and the critical temperature decreases to 0. And this experiment measured the superfluid density by measuring the mutual inductance between two coils of wire. And that measures the penetration depth of the magnetic field, which gives you a direct measurement of the superfluid density. What they found is that as you move on the phase diagram in this direction, the superfluid density drops off dramatically. This is despite the fact that we don't expect the total charge density to change very much. And because the total charge density is just the sum of the superfluid density and the normal density, this would suggest that the normal density at 0 temperature is actually increasing. It's not 0. There's another part of this experiment which is kind of interesting, which is that as you go to 0 temperature, the superfluid density goes to a constant, but it does so linearly with the temperature. And a linear temperature dependence is in violation of any BCS or dirty BCS type description for this. So that study was followed up by this paper in 2018, who measured the superfluid and normal densities using a different method. They measured the optical conductivity. And when you measure the optical conductivity, as we'll see, that gives you a direct measurement of both the normal density and the superfluid density independently. And so here in this plot, they've plotted in terms of the critical temperature. So increased doping is moving to the left. This blue curve is the normal density. This green curve is the superfluid density. And you can see that as you increase doping or the critical temperature goes to 0, the normal density, these are all measurements at 1.6 Kelvin, which is well below the critical temperature. So in effect, this is like the 0 temperature data. The normal density is going to a constant, and it just gets larger and larger. And in addition, they were able to do something kind of interesting, which is that they made these measurements of the superfluid density and the normal density, and they summed them to give the total density. And then they're actually, by using a magnetic field, they can suppress the superconductivity, in which case they can compare the sum of these two values given by these orange dots to the normal density, which they measure in the state without a superfluid or without a superconductor. And you can see that, so this Sn is what they measure without the superconductor. You can see that the sum of these two is very close to the normal or the total charge density. So again, the superfluid density is decreasing dramatically as we move to overdoped, and the total charge density is not changing very much. Okay, so we go back to this equation and we say, well, rho n of 0 vanishing seem natural, but if it doesn't vanish, then it means that this combination has to vanish. And that would suggest that fluctuations in the normal velocity and in the Goldstone are not independent. A priori, that seems a little odd, but it turns out that actually that's very natural. And the reason is that it's necessary for the susceptibility matrix to obey Onsager relations. So I wrote two of the fluctuations here. The first is the fluctuation of the momentum, which can be written in this form. The second is the fluctuation of the Goldstone. And here I've written things in a very suggestive way, which I just added and subtracted the normal velocity fluctuation. And the reason I did that is because we know that the normal velocity acts as a source for momentum, and the susceptibility is just given by the total enthalpy, which is mu rho plus st, where here you see that the coefficient of delta U is actually mu rho n plus st. So in order to turn this expression into something that's mu rho plus st, we need to add and subtract mu rho s times delta mu, which means that I can write this as h times delta U plus rho s times, or sorry, mu rho s times this combination. And then you can check that when you do that, the susceptibility matrix becomes symmetric. So that means that the source for the goldstone is not just delta C, it's really this particular combination. And because in the background we have no net superfluid velocity, that means we don't have a source, and so we should expect that the fluctuations are actually aligned. Now, if this is true, that means that this expression always vanishes whether rho n is 0 or not. So actually, while at first it may have seemed that this expression is very constraining, it would have been very surprising if hydrodynamics was actually able to tell us what rho n of 0 should be. To actually find rho n of 0, we need to know the equation of state. And again, we only have these few examples experimentally, and most of them seem to point towards a rho n which vanishes. And so we would like other systems that we can understand well to see when and if we can actually have a non-vanishing normal density. And that's where holography comes in. So since this is the hollow tube, I don't think I need to explain holography in much detail, but maybe I just will give you our philosophy in using holography. And the point is that we know that the hydro regime of certain strongly coupled quantum field theories, specifically holographic quantum field theories, is dual to the near horizon physics of certain black holes in anti-de Sitter space. In this context, the radial direction of the anti-de Sitter space parameterizes an RG flow, which goes from some symmetric, relativistic, invariant quantum field theory in the UV to some IR fixed point, which may have broken symmetries. And this IR fixed point might be described by some quantum critical point or phase. And what I mean by that is that the correlation functions can be described in terms of certain critical exponents. For instance, Z, the dynamical critical exponent, which gives a relationship between the scalings of time and space. Theta, which is the hyperscaling violation parameter, which tells us what the effective dimension of the system is at the IR fixed point. D, the spatial dimensions, and then gamma, which is any anomalous dimension for some symmetric operator or symmetry preserved operator in the UV. And finally, if it is the case that the IR of these systems is quantum critical, well, that's good because we expect that quantum critical systems in some sense are universal. And so ideally, if we have some holographic system which flows in the IR to some critical phase, that critical phase, or the observables in that critical phase, can also describe systems who may look very different in the UV but flow to the same critical phase in the IR. So maybe this is the cuprates or strange metals or some other system. So it's in these critical phases we want to understand the properties of holographic superfluids, and then ideally these may be able to describe real-world systems. Okay, so the model we're going to use, I'm going to write in a very generic way in this expression. This model can describe lots of different holographic superconductors, depending on what fields are turned on and what the form of the potentials are. So for instance, it can describe the original holographic superconductor if we turn off psi. Here psi is a neutral scalar. If we turn it off, then we just have this covariant derivative term and a potential for a complex scalar, plus, so Z will go to 1 in this case, plus a field strength for a U1 field. That would describe the original holographic superconductor if the potential is just a mass term, or we can have the potential be quadratic, which is going to be the case, or sorry, quartic, which is going to be the case we're interested in, so that it's bounded from below. And in that case, the system can flow from some relativistic invariant phase in the UV to some phase in the IR, which may have Z, the dynamical critical exponent, greater than or equal to 1, depending on the behavior of the Maxwell field in the IR. If we let psi be non-zero, then it runs in the IR, And for certain phases, its running makes this coefficient blow up. In that case, z will be greater than 1, and we will have a violation of hyperscaling. If, on the other hand, its running makes this function go to 0, then you can see that the gauge field becomes irrelevant in the IR, and z goes to 1. But again, hyperscaling is still violated. And between these two phases is a phase which we'll call the critical phase, where the scalar minimizes its potential. Psi goes to 0 on the horizon at 0 temperature, and the phase has z equal 1 and theta equal to 0. Okay, so the next couple of slides are going to be a little technical, but what I want to convince you is that when we use holography, we can actually calculate rho n analytically. And so I'm just going to go over the derivation. If you will excuse maybe 5 or 10 minutes of some technical, very equation-rich slides. So to start, we're going to make an ansatz for the metric in the field, which has just a radial dependence. So our system is translation invariant and rotation invariant. We're going to write eta here as the modulus of the actual complex scalar eta, which means we can just consider it as a real field. And then just keep in mind that the metric GTT is D, GRR is B, and the spatial metric is C. As we're probably all familiar with, to calculate the conductivity, what we do is we perturb the system with some infinitesimal electric field, which we can write in terms of the gauge field in this way, and that only sources this GTX metric fluctuation. Then we know that the conductivity, the optical conductivity, will be given by a ratio of the subleading falloff of AX to the leading falloff. This I omega AX is just the electric field. And from our hydro equations, we can derive that we expect this to be given by just a pole in the imaginary conductivity at leading order in the hydro, with a coefficient which has this first term, rho n squared over mu rho n plus st, and the second term, which is really rho s over mu. So there's two pieces that contribute to the pole. To find rho n, we just use our earlier relation that rho n plus rho s is rho, and here we know everything. We know rho from the subleading falloff of the Maxwell field. We know mu from the leading falloff, and we know s and t from the behavior of the metric at the horizon. And so by finding the conductivity, we can find rho n just by inverting this. Another thing to notice is that because it's just a pole, that means that we can actually solve the AX equations in the omega goes to 0 limit, which simplifies things. Okay, so the two fluctuation equations we get are these. I'm going to look at this one first. Here, this equation can be solved exactly for GTX in terms of AX. And if you look at the asymptotic falloffs in the UV of these two functions, this is going to be proportional to fluctuations in the momentum. This is going to be proportional to fluctuations in the Goldstone, because again, if we choose a gauge in which AX is equal to CX, you can see that this is just fluctuations in the, or sorry, minus CX. You can see that this is fluctuations in the momentum. And then in order for this relation to hold or to be 0, that actually requires that the fluctuations obey exactly the equation we saw earlier from hydrodynamics. So that's a nice confirmation. Then we look at the AX equation. And the important part of this equation is that there's two effective mass terms, and they both come from different symmetries being broken. So this part comes from breaking particle hole symmetry by introducing a finite charge density. And this term comes from breaking the U1 symmetry when the eta obtains a finite value. So there's a condensate. And these two terms will compete against each other actually to determine whether or not rho n vanishes or not at 0 temperature. And I'll show you how in a little. Okay, so in this form, this equation is kind of messy. And it doesn't look very easy to solve. We can use an identity of the background fields, which is this identity. It comes from the scale symmetry. And it's just, this left-hand side is just equal to a constant, which is minus the entropy times the temperature. So after a little bit of algebra, we can rewrite our AX equation in this form, which looks somewhat messier, but actually it's quite a bit nicer, because here the only explicit dependence on eta is on the right-hand side, and the left-hand side is a total derivative. Here I've introduced a function R of R, which is just the electric flux. When eta vanishes, then we can actually solve AX exactly. In that case, R becomes a constant. And probably a lot of you are familiar with the solution, which tells us that the ratio of AX1, the subleading falloff, to the leading falloff is just given by rho squared over ST plus mu rho, which is the familiar pole in the optical conductivity for translation invariant charge systems. Later, we're going to look at this in an expansion in ST, so just keep in mind that we can write this as rho over mu plus an expansion of this form, a sum of terms that goes minus ST over mu rho to power n. When eta is not 0, this equation cannot be solved exactly, but at low temperatures, we can use ST as an expansion parameter and solve perturbatively in ST. So here I just rewrote the equation in terms of this function curly a, which is the AX over AT we saw earlier, but I've divided by their UV values. And again, we write this perturbatively as an expansion in ST. The leading order term at order ST to the 0 is just 1. That's because we've divided by the UV pieces. And that means that the subleading pieces all have to vanish at the UV boundary so that AX becomes AX0 at the boundary. Then you can solve the higher order terms in terms of the lower order terms, because you can see that this piece, this piece here contains no explicit ST, whereas these pieces do. So this piece can be solved in terms of the lower order terms. So the first expression, the first term is of this form. The second term contains, second order term contains a lot more pieces. But the important point of this is that because of this total derivative, there's a free constant at each order in the expansion. And up to this point, we haven't determined what this constant is. So how do we determine it? Well, X should be regular in the omega goes to 0 limit. And that means that the limit that R goes to the horizon of the gauge field times this curly A, this is just AX times some constants, should be a constant. But what we see in the presence of these CIs is actually it's a constant plus something that's divergent. And this divergent piece may be familiar to those of you who have seen calculations of the so-called incoherent conductivity, which is the conductivity when momentum is not conserved. There, to find sigma q, you see that there's two pieces, one of which is regular at the horizon, the other of which is irregular at the horizon. It diverges, and it's the coefficient of the irregular piece which determines sigma q. Here, the constant piece is coming from the regular solution, and this divergent piece is coming from the irregular solution. Now, this looks like a problem, but because there's a new constant introduced at each order in the expansion, it turns out that the higher order terms in the expansion can cancel the lower order divergences. And that means that all of these constants, Ci, can be written in terms of C1, so we really just need to determine what C1 is. Now, the way we do that is we consider this pole in the optical conductivity. So recalling the definition of this curly A, if we look at the derivative of curly A as we go to the UV boundary, it has this form. You can see that this piece is AX1 over AX0, so that's going to be proportional to the pole in the imaginary conductivity. And then this piece, the AX0, cancels, and you get something that's minus rho over mu. And then if we use our earlier solution, we can write this perturbatively in ST, which has this form. So at order ST over mu, we get 1 plus that constant C1, then at ST squared, again, 1 plus C1, but there's a new term, which is some integral I, that depends on the condensate. So for instance, if the condensate is 0, then, well, what happens is that if we look at this integral depends on a competition between what I showed earlier, these two mass-like terms. And it turns out that if the condensate contribution is more relevant than the particle hole breaking contribution, this integral actually diverges, in which case we need to cancel. So it diverges as the temperature goes to 0, or in the way we've parameterized things, as RH goes to infinity. When it diverges, we need to cancel the divergence using this constant C1. So if we go back to the case with no condensate, well, obviously this integral converges, it's just 0, and so we can set C1 to 0, in which case we see that this piece goes away, C1 is 0, and so the pole in the imaginary conductivity is given by rho over mu times an expansion in powers of ST over mu, ST over mu rho. But when we have a condensate, we have to be a little more careful. So again, when it diverges, when this integral diverges, we use the constant C1 to cancel the divergence, which means that C1 is just given by minus the metric function d, which is GTT over C, which is the spatial metric function, at RH, but we use the 0 temperature metric so that it's really only in the limit that the temperature goes to 0 that the divergence actually appears. And this combination is actually the transverse speed of light, so the speed of light along the spatial directions, which we can write as minus CIR squared. On the other hand, if this is the dominant piece, then the integral converges and we can safely set C1 to 0, in which case we just have ST over mu squared plus ST squared over mu cubed rho plus ST squared over mu squared times some constant as the temperature goes to 0. Okay, to actually find when this competition, what wins in the competition and when the integral diverges, we need to know a little bit more about the IR phases. So as I said earlier, there's two cases we want to consider. One is when we actually set the neutral scalar to 0. When we do this, the flux, the electric flux from the horizon always vanishes in the IR. All charge goes into the condensate. And we can write the metric in this form. So this is at finite temperature. But the main point is that basically everything goes like 1 over r squared except for GTT, which goes like 1 over r to the 2z. Z is equal to 1 if the scalar minimizes the actual potential, in which case you get an emergent scale invariance. And the CIR that I defined earlier is just given by the ratio of the constant LT over, sorry, there should be an LX here, over LX. The entropy just goes like the temperature to the spatial dimension, and the Maxwell field scales anomalously, which means that really the electric field strength is irrelevant in the IR. It's not necessary to support the IR geometry. On the other hand, if the scalar minimizes its effective potential, then Z is now greater than 1, which means that there's an emergent Lifshitz symmetry, so that time scales with a power of length to the Z, whereas space scales like a power of the length. And that means that this speed of light, the CIR we defined earlier, is again given by LT over Lx, but now there's a power of RH, which means that there's a temperature dependence. And furthermore, the Maxwell field actually supports the IR. On the other hand, when we turn on the neutral scalar, then the flux in the IR can be non-vanishing. And that's the case when the function ZF, the coefficient of the field strength term in the action, goes to infinity, or it can be 0, which happens when this ZF goes to 0. And to go between these phases, what we do is we source the neutral scalar in the UV. And so here, I've plotted the electric flux on the horizon in terms of the neutral scalar source in the UV. For very large source, large positive source, ZF will go to infinity, but actually, if ZF goes to infinity too quickly, the system doesn't support superfluidity, and now all of the electric flux is sourced by the horizon, rho is a constant. But as you decrease the source, eventually the system can allow superfluidity, and some of the charge goes into the condensate, and as you keep decreasing the source, more and more goes into the condensate until you get to a critical point beyond which all of the charge is in the condensate at 0 temperature, and none of it is sourced by the electric field. Sorry, there's no flux by the electric field. Sometimes you might hear me call these phases fractionalized and these phases cohesive. And at the critical point, this is that point I described earlier with Z equal 1 and theta equal to 0. Now, an important part of this analysis is actually that the complex scalar eta is irrelevant. All of these phases, well, okay, not exactly this plot, but the actual phases, the metric, for instance, exists whether or not there is a superfluid. And the metric can be written in this form, which is like what we saw earlier, except for there's this extra scale covariant piece, which includes the hyperscaling violation parameter. Yeah, finally, if Z goes to 0, this is like the Z equal 1 cases we saw earlier. The Maxwell field is irrelevant in the IR, and we have Z equal 1. Okay, so again, everything is described in terms of Z, D, theta, and any anomalous scaling. And so now we can look at our integral in terms of our Maxwell field and our metric functions, and we find that for Z less than the spatial dimension plus 2 minus theta, that the integral actually diverges, in which case, as we said earlier, we need to set the constant to some non-zero value, which cancels the divergence. It's just this minus CR squared. Then, using our earlier expansion, the first few terms can be written in this way. And in particular, the coefficient of ST over mu squared includes this 1 minus CIR squared, where for Z not equal to 1, CIR has some temperature dependence. For Z equal 1, it does not, it's some constant. But this temperature dependence is more relevant than ST, which means that we don't care about the order ST squared terms. Then if you expand this expression we got earlier, here I've written it in a more suggestive way. If you expand this, you see that this implies rho n is given by ST times 1 minus C squared over C squared, which is exactly the expression we saw earlier for the eta to the 4th theory, or for conformal theory in the quantum effective action. This has a temperature dependence because of the CIR of this form. And you can see that when Z is less than D plus 2 minus theta, this goes to 0 as the temperature goes to 0. And here I have, excuse me, some numerical data from the model we described earlier. Here we've set the neutral scalar to 0. This gives a critical phase in the EIR. And you can see that for Z equal 1, theta equals 0, rho n scales exactly like ST. Remember, in this case, CIR is a constant. And in addition, the coefficient you can check actually is 1 minus CIR squared over CIR squared. Here we have a cohesive phase, so the hyperscaling violation parameter is not 0. And again, you can check using this formula. These are all in D equal 2, that rho n goes like T to the 4th and vanishes at 0 temperature. And finally, here's a Z equal 2 phase, which should vanish linearly with the temperature, which it does. There's a slight subtlety if you're looking closely, which is that there's two different types of points on this plot. The circles are the clean translation invariant system. Later, we'll break translations weakly. This shouldn't change the value of rho n or the behavior of rho n, but it actually allows us numerically to go to lower temperatures. So this just helps us confirm that, in fact, we see a linear in temperature scaling. Okay, for Z greater than D plus 2 minus theta, well, in the earlier slide, this would now diverge. What actually happens is that the integral goes to a constant, and so we can safely set C1 to 0. And then our expansion has this form, where this rho n of 0 is a combination of rho of 0, the charge density at 0 temperature, plus the value of this integral, which is now a constant at 0 temperature. And what that means is that at 0 temperature, rho n actually goes to a constant. And so here are some numerical plots. The first one has Z equal 4, theta equal minus 3. The dashed line is rho in, and the dotted line is rho n. So this is the flux from the horizon. This is the normal density. Both go to a constant at 0 temperature. Here's a phase with Z to infinity, theta to minus infinity, but their ratio held fixed. Again, rho in and rho n go to some constant. Here's a so-called semi-local quantum critical phase, which has Z to infinity, but theta equal to 0. And in these phases, actually, rho in and rho n also go to a constant. But rho in, the flux from the horizon, does not have to be a constant in order for rho n to be non-zero. So here's an example, a Lifshitz phase with Z greater than D plus 2 minus theta, well, theta 0, Z is 12. And the dashed line, again, is rho in, it goes to 0, but rho n goes to some constant. So now let's go back to the Coupe experiments. We've established that there are systems, holographic systems, for which we can control everything.
Yes. Can I ask you a question? I got lost in the, so in the previous slide, when you're saying that rho in goes to 0, but rho n does not go to 0.
Yes.
In the last sequence.
Yes.
So rho in is the flux coming out of the horizon.
Yes.
So then the charge, where is it coming from?
It's all in the condensate.
Okay.
Yes. So if you look at this integral.
But if it's in the condensate, should it contribute to rho n or rho s? I'm confused.
Oh, well, it contributes to both. I mean, because rho n is the sum, or it's the difference of rho and rho s.
Okay.
The point is that if rho n goes to 0, another way to say that is that all of the charge density, at least in the hydrodynamic description, is in rho s.
Yeah.
That doesn't have to be the case. Yeah. And yeah, so just to kind of follow up on your question, in this integral, this blue term is actually proportional to rho in squared. And this makes it look like if rho in vanishes, that the integral is going to blow up. But actually, there's a kind of subtle competition between the metric functions and rho in. So you can have this integral not diverge at 0 temperature. Specifically, when z is greater than d plus 2 minus theta.
I see.
So that's kind of a subtlety, yeah.
Thanks.
Of course. Okay, so we've shown that rho n doesn't need to vanish. And now let's see what the consequences of this are on transport. And so for cuprates, they're not perfectly clean, so they very weakly break translations. We can do that holographically by introducing linear axions where we know what the relaxation rate is exactly in terms of the background fields. And when we break translations, the conductivity has a form like this. So it has a Drude form plus some pole in the optical conductivity in the imaginary part that's proportional to the superfluid density. And we can again use now this form, since we know gamma exactly, to calculate rho n and rho s. And this plot just shows that using this form, but with broken translations, we get the exact same value for rho n as we did in the clean case. So here the dots are the clean data. The curve is data with very weakly broken translations. So roughly gamma is proportional to m squared. Here is, so this is a case with z equal 1. This example has the z to infinity, theta to minus infinity, but the ratio held constant. And here, okay, so this curve, the dots are the clean data, the dashed line, the dotted line is the translation broken case. And again, they agree exactly. The other curves, I have only included the translation broken case, and they have different values for the neutral scalar source, which you can see acts like doping because it changes the value of rho n. And also, in addition, it moves you closer or further from the two quantum critical points. Okay, so using this value of the scalar source as a doping, we can try and make some plots which look similar to this. So again, now the conductivity has a Drude form. Here, what they've plotted, this is from the Mahmoud paper. Here they've plotted the real part of the conductivity, and they fit it to a Drude form. The orange line is the high temperature data above the superconducting transition. And the blue line is the quote unquote zero temperature data or very low temperature data. And the difference between these two lines, the gray shaded region, tells you how much of the charge density is moving into the superfluid phase, into this imaginary pole. And so as you go to more overdoped, the critical temperature decreases and less of the charge density is moving into the imaginary pole, and that's how they get this curve here. Here we do the same thing. So again, I'm going to use minus 0.325 and minus 0.425, these two curves. So as you move this direction, you are lowering the critical temperature, and the normal density should be increasing the zero temperature, which means that less of the activity is moving into the pole, and that's exactly what you see. So going from this way to this way, the difference is much more extreme. And here, so this curve up here is above the critical temperature, here's below, again, above and below, and the lines are the hydro calculation where we use the rho n value from here, from the clean data. So we find rho n from the clean data, we know the relaxation rate, and then we just plot the Drude form. We plot this expression, and then the dots are the actual numerical data, and you can see that they agree exactly. And then we can make a plot very similar to this, although it's actually kind of mirror image because you can see the critical temperature is moving to zero as we go to the right. This is the normal density, it's going to the total charge density. There's a slight difference, which is that actually the total charge density is slightly smaller when you have the superfluid than when you don't. So this rho T NS, we can also suppress superfluidity. As I said earlier, the condensate is an irrelevant deformation. So the phases actually exist with or without the condensate. It turns out that, that there was evidence for a non-zero normal density well before these transport measurements through the specific heat in terms of what's called the Sommerfeld coefficient, or if you look at the specific heat, there's a linear in temperature contribution whose coefficient tells you roughly how many normal electrons there are in the system. And so, again, moving to the right, this is an experiment from 2004. Moving to the right, the normal density, or really this coefficient, increases dramatically around a doping of 0.22, goes above this blue curve, and then starts decreasing. This blue curve is the same materials, but with super conductivity suppressed. And so this is kind of a measurement of the total charge density at zero temperature with no superconductivity. And you can see that they approach each other. The normal density with the superconductor approaches the charge density without the superconductor. Here we do the same thing. We chose theta, or sorry, z to infinity, theta to minus infinity, and z over theta fixed so that we had a linear in temperature specific heat, but you could consider just any coefficient of the specific heat in a fractionalized phase as a measurement of the normal density, and we can produce a very similar plot. And what's going on here is actually this black square is the critical point where you switch from a fractionalized to a cohesive phase, in which case the specific heat no longer scales linearly with temperature. And as you approach this, first the normal density increases and then drops off dramatically as you get very close to the critical point. And that's just a signal that as you approach this critical point, the normal charge density, which is non-zero at zero temperature in the fractionalized phases, drops off dramatically. Finally, using our results, we can go back through the holographic literature and explain some of the results that were a bit perplexing in the past. So, for instance, if we look at the original holographic superconductor, Sonner and Withers showed that this model obeys the two-fluid hydrodynamics. And here are some plots of the superfluid density compared to the total charge density for large charge. Here, zeta is actually the net background superfluid velocity, but for sufficiently large charge, this doesn't play a role. And while the original holographic superconductor is not quantum critical in the IR, you can still use the method we used, and you can show that the integral will diverge, which means that we need to include a factor of CIR. And here you can see that actually CIR, this is a power 2, this goes like r to the power 2. And so CIR is a constant, and rho n is just going to be given by this ST times this combination of speeds of light. Finally, you can look at more transport observables. So for instance, if you look at the dispersion relation, you see that actually there's a number of sound modes. One of the sound modes is called second sound. It's a sound mode that rather than transporting pressure, transports heat. And it has this expression. The important part of this expression is that this st plus mu n appears in the denominator. And so this will have very different behavior whether or not rho n vanishes or not at zero temperature. So if rho n vanishes, this actually goes like the CIR squared, which allows us to identify it roughly with the superfluid sound speed. And because when z is not equal to 1, this has some temperature dependence, C2 can vanish at zero temperature. But if rho n is not 0, then this just goes to a constant, this denominator, and C2 goes like, C2 squared goes like ST. There's also the fourth sound, which is a sound mode when you suppress the normal flow. And it has this form. In particular, it goes like 1 over d, but it has a coefficient which depends on the normal density. So if the normal density is not 0 at 0 temperature, then the fourth sound will actually be less than 1 over d. And for these systems, which are conformal, 1 over d is the critical velocity, the Landau critical velocity, and it's also the adiabatic sound speed. Okay, so here's examples in d equal 3 from this paper. This is a plot of rho s over rho. This should go to 1 if the normal density vanishes at 0 temperature, and be less than 1 if it doesn't. And you can see that in most cases, for large q, it does vanish, but for small q, it does not vanish. And that is an indication that rho n of 0 is not 0. You can actually check, you can calculate what we expect the IRs of each of these curves to be. And for this curve, we expect that it's actually one of these cases with, it's a Lifshitz phase with z greater than d plus 2. And here, d is 3. So this has z greater than 5, but all of these cases have z less than 5. Well, actually, the q equal 2, it looks like it's going to 1, but it turns out it has z greater than 5 also. And you can see that here in the second sound, because these two curves look like they're going to 0 rather than to a constant. All of these curves have z equal 1, just like these curves, so they should go to some constant, but these look like they're going to 0. And it turns out that they go to 0. Well, you can use this to measure what z is, and specifically this curve has a rho n, which is not 0. And finally, in this plot, the red line is the adiabatic sound speed, which is 1 over d. So d is 3, this goes to 1/3. The green line is the fourth sound speed, and the blue line is the second sound speed. And you can see that, for instance, the green line doesn't approach 1/3, which is another sign that rho n is not 0 at 0 temperature. Okay, so to summarize, the perspective is that holographic superfluidity, at least, is an irrelevant deformation around some underlying quantum critical ground state, like we saw in the cohesive and fractionalized phases, where eta specifically doesn't actually support the IR geometry. And from that perspective, then the normal density at 0 temperature can actually be determined from properties of this ground state. It depends on a competition between two broken symmetries. When the broken symmetry associated with condensation is more important than the broken symmetry associated with a finite charge, then rho n goes to 0. So this is the case when the integral diverges. On the other hand, if things are switched, then rho n doesn't go to 0. I didn't talk about it, but the integral actually determines what the subleading temperature dependence is. And so you can use this to find what appropriate z's and thetas are if you want to actually match the LSCO data. Like I said earlier, it is related, but it turns out that the flux from the horizon doesn't actually determine the normal density. And this is actually maybe something we should have expected, because even in real world systems, rho n isn't necessarily capturing what's going on microscopically. For instance, in BCS superconductors, lots of the electrons don't ever see the superfluid. Finally, there's some more transport observables we didn't talk about, but if you let the fluctuations have some momentum, then if you look at observables transverse to that momentum, for instance, the transverse diffusivity from hydrodynamics, you can find that it has this form where it depends only on the normal enthalpy. So the rho s doesn't show up in this expression. And what that means is that this really depends on the value of rho n at 0 temperature. If rho n vanishes, then we know holography tells us how to find eta, and we find that 4 pi temperature times the diffusivity gives CIR squared. Whereas on the other hand, if rho n doesn't vanish, we get the diffusivity being proportional to the entropy over this normal density at 0 temperature. But if you remember the previous slide, each of these expressions is roughly the second sound speed of the superfluid. And so, there's been a lot of discussion in the past about a universal speed for diffusivity. And this may or may not be surprising, but it seems like this is pointing towards the second sound speed as being kind of the appropriate speed to use for holographic superfluids. Finally, we talked about using a quantum effective action for finding rho n, but the quantum effective actions we used earlier are only appropriate for z=1 phases, where we expect that the frequency goes like the momentum just to the power 1. On the other hand, Lifshitz phases, we expect the dispersion actually to go like the momentum to the power z, and it would be nice to actually write down an effective action that captures this and see if we can prove from the effective action that the normal density doesn't vanish for z greater than d+2. And finally, essentially everything we said was for 0 relative velocity between the superfluid and the normal fluid. And it's an interesting question to ask what happens if we introduce a finite background superfluid velocity. In some respects, we don't expect things to change dramatically, at least in terms of the normal density, because like we showed here, here you can calculate for 0 superfluid velocity, you get just this metric, and this remains a solution with maybe different values of Lx and Ly when you have finite superfluid velocities, at least for small enough superfluid velocities. You can also consider transverse fluctuations, in which case this background velocity may not play a role. But again, this is an open question. It's something we're working on. Okay, so that's it. Thank you.
Thanks a lot, Eric. So let's see if we have questions. I have some time for questions. So whomever wants to ask a question, please just unmute themselves and ask.
I have a question.
Yep.
Yeah, thanks for the nice talk, Eric. So yeah, it's about this normal density staying finite at 0 temperature. So this really relies on trusting these solutions down to 0 temperature.
Yeah.
And on the other hand, these days people talk a lot about weak gravity conjecture and so on, and extremal black holes are expected not to be stable. So do you have any comments on that?
My only comment is that's something we're also, a little worried about. We don't really expect that. Well, it's not clear that these ground states that I've described are stable, but it's really most of the discussion is talking about finite but very low temperature where all the experiments occur. Yeah, I don't really have too much to say about the actual 0 temperature state. Ideally, we would have a stable state where we could say something specific, because that's really where we want to think about this effective action.
Okay, thanks. And another question I had is so these EFT predictions for vanishing density, at least the ones I'm familiar with, assume translation invariance.
Yes.
And as you point out rightly, that's definitely not the case in the cuprates. The Leggett arguments, do you know if it assumes translation invariance?
Yes, it does assume translation invariance.
Okay.
But again, well, okay, so we know at least from the holographic calculation, we don't expect that, at least if you break translations weakly, things should change very dramatically. So that's what this slide is kind of showing, is that you can use the translation invariant case as a guiding principle, and if you break translations sufficiently weakly, then all that happens is that you get a real contribution to the conductivity, which has a Drude form, but the densities themselves don't seem to change dramatically.
I see. Thank you.
May I make a quick comment to answer Luca's first question?
Yeah.
I think that the fact that for the z=1 phases, we recover holographically the exact prediction of the EFT, including for cases where we don't really trust the holographic ground state, so where there is a running scalar and a non-zero hyperscaling violation exponent, etc., sort of, I mean, gives some measure of confidence that the calculation works in this case. And so maybe this can be extrapolated to Lipschitz phases.
I see.
Any more questions? Maybe a small question. Whenever you ask about breaking translations, you were considering talking about disorder, so explicit breaking. Would all this like work the same if you have spontaneous breaking? Like charge density waves?
Yeah, there you have to be more careful, because you'll have another Goldstone to worry about at low temperature. So I don't know, that's an interesting question. We didn't really look into that. Yeah.
Thanks.
Yeah.
Okay, so we've been more than an hour, I don't know, but okay, of course, if somebody wants to ask questions, please. Yeah. It looks like nobody's asking. Okay, then let's thank Eric again. No clapping, but we thank you. And no, it was very nice talk. Thanks a lot. And sorry again for the misunderstanding with the starting time. So I wrote down in the chat that next talk is in a week from now, but it will be at 4 Central European summertime. And also please do subscribe to our mailing list if you want to be updated about what's going on. So with that, this is all, and thanks again a lot, Eric.
Thanks.
See you all soon. Ciao.